Yeah, that'd probably be good. A 5-minute warning before the end probably be good. Please end, thank you.
All right, any questions?
I have one on the master set, but if I can find it. Number 7, do you have it below?
Yeah.
Number 7, part B, what is the force on Q2? I don't really know I don't know if I did it right.
These are in equilateral triangles, so you would find the force on 2 from 1 and from
Yeah,
3.
I did that, I got both of them, and then from there, I wasn't sure where to go. After I got the force from 1 on 2, and
Then it's vector addition.
so you don't just like simply add them, those two?
No.
Yeah, you gotta do that cosines and,
Yep.
okay. So it's that number cosine times cosine 60, sine 60. And then you find the magnitude
Of the components.
so like you add them, square them, and square root them.
Oh, to get the magnitude of
Yeah.
Well, in part B, when I say what is the force on Q2, force is a vector. So if you want to express that force as a magnitude, you also need to provide a direction. Or if you define I hat, J hat, and give me the answer in rectangular form, something I hat plus something J hat, that works too.
Okay.
That's why if you love the math, you can take the extra step.
Okay.
Who doesn't love the math, right? One of those that 4th grade math teacher taught. Flashbacks. Doing long division. Do every other problem. I would do the odds just so that it'd be one fewer to do.
I've had to relearn long division multiple times. I'll relearn it and I'll forget it again, and I'll relearn it and I'll forget it again.
I haven't forgotten it, it's just a matter of, if I know how to do it, and I can demonstrate I know how to do it, then why do I have to do 20 of them? The thought of using a calculator was not,
So you don't forget it, I guess?
well, I didn't.
What about part C? Cause I didn't even see part C.
Part C, the electric field, so that's just you have to worry about direction. So charge 2 is on the x-axis.
Yeah.
Charge 1's at the origin. Charge 1 is negative, so it'll be pointing towards the origin. And then it's just straight up like a jug.
Okay.
Just make sure you're in the right units.
Okay.
Is that sufficient?
Yeah.
Okay. Any other questions? All right, when we last left off, Gauss's law of electricity. Gauss's law of electricity. Let's actually use it. This is the shortest form of it. You can also write it as integral E dot A is equal to Q enclosed over epsilon sub naught. And then there's some other forms, but that's sufficient for what we have. Oops, that is small error there, E dot dA. It is an integral, so I need a differential there. The circle means it's over a closed surface.
So there's no limits of integration? Is that what that means? Wait.
Well, I mean,
You said it's
ultimately,
an
once
integral.
you narrow it down to a single variable other than area, then you'll put limits of integration in at that point.
What does it say next to the Q?
Next to, that's E and C for enclosed. It's the charge enclosed in that surface.
Is this symbol on the left an integral symbol with a circle in the middle, or is
Yes.
it like a whole separate symbol?
No, it's an integral. The integral, you'll be doing it, you're doing an infinite sum. And the circle means you're doing, since it's over area, you're doing the integral over the entire surface.
Okay.
Without that, then it could be just part of the area.
It's not just from like 1 point to 1 point, but over.
Yeah, it's over, yeah. If you see this and it's dot DL or something with a one-dimensional aspect to it, then that would be, the circle would mean it's a closed loop, and you're doing a line integral over the entire loop.
That's not what this is.
No, this is over since it's with respect to the area, we're talking the surface of a three-dimensional object.
So you just kind of have to know, like,
Yeah.
whether it's 1 dimensional or 3 dimensional.
Yeah, I mean, from context. Well, typically you're creating the Gaussian surface, you're creating your virtual surface that you're doing the integral over, so you know whether it's, it's three-dimensional because you created this virtual. Why don't we do an application, perhaps that will allow it. Remember that integral is just a sum. It's a infinite sum of infinitesimal parts. I'm going to do an infinite line of charge. And I want to know the electric field at this point. I'll call that point P. Uniform linear charge density. This distance here, I'll make R. When we did this problem before, well, one, we found force, but when we did the problem before, we ended up doing calculus. But instead, we're going to use Gauss's law. So what I'm going to do is I'm going to create a virtual surface. Gauss's law works best when you're dealing with some symmetries. So what I'm going to do is I'm going to create a virtual surface of a Gaussian cylinder. So I have a Gaussian cylinder here of radius, well, it'll have to be the same as R because I want that point P to be right on the surface of my Gaussian surface, my Gaussian cylinder. The length here is L. And that's all we need. All right, so the surface this cylinder doesn't actually exist. We're using it just as, well, again, it's a Gaussian surface. Gaussian surfaces are by definition a virtual one. But I know that the flux through this surface, though, is equal to the charge that's within it. Well, so I'm going to plug into basically here. Now, my emphasis that this is just a sum is I'm basically going to find the electric flux through each end cap and then the sides. I know that for symmetry reasons, the electric field, we will naturally just assume that this linear charge density is positive. If it turns out it's negative, it doesn't change the formula, just there's a minus sign that will show up in a minute. I know the electric field has to be going in that direction because of symmetry, because this point is going to create an electric field in that direction, this point will create an electric field in that direction, the horizontal components would cancel out. So the electric field is pointing away from the line. So this part of the equation here is, this is going to be the electric flux through the left cap, plus the electric flux through the right cap, plus the electric flux through the side. That's going to be equal to the enclosed charge. Well, linear charge density is dQ dL, or Q and car closed over L. So again, I have some charge here of Q and closed. That's gonna be equal to the length of my cylinder times lambda over epsilon sub naught. Next step. What are the direction of the area vectors? So for the left cap, what's the direction of the area vector?
Up to the right.
To the left.
To the left. So if my area vector on the left cap going this way. What about on the right cap?
To the right.
And what about at point P? What's the direction of the area vector? Right? It's already inside over there. So anywhere, because if you recall, for a closed surface, the area vector points outwards. It should be perpendicular to the surface. And so area vector is perpendicular to the left side, means it points that way, to the left, on the right points to the right, and on the body it's just pointing away from the line. Matter of fact, it points in the same direction as the electric field. You can go through the calculus of it, but in essence, no matter where I am, my electric field at any point on that side is the same direction as the area vector. So, well, we'll get to why that's zero in just a second. So this is just going to be the electric field at whatever it is at that radius r times the area of the side. Now the left cap and right cap, what are these equal? And follow-up question, why?
0.
Why?
Because they both go the opposite way and for infinitely amount of time.
Not because they're going opposite directions.
Cancel out.
Pardon?
Like cancel out.
No, they do not cancel each other out. Each is 0 in its own right.
Is it because it's not having any effect on P? It's not having any effect on P because
There's a math reason for it.
it just gets smaller and smaller until it's 0.
So R is some distance away from the line, so we're not letting R become infinitesimally small. What are dot products? What's a dot product?
Oh, because it's perpendicular.
Yes. The electric field is going away from the line. No matter where I am, the electric field is going away from the line. The area vector is parallel to the line. So there, my electric field and my area vector are perpendicular to each other. So these are 0 because anywhere on the end cap, the electric field is perpendicular to the area. So after all of that, we can eliminate those. The only thing we're left with is this, and that's equal to L lambda over epsilon sub naught. What is the area of the side?
That's a calculus surface integral thing.
Geometry. You don't have to use calculus for this. It's the surface area of the cylinder, of the side of the cylinder.
Oh, it's the area of the circle times the height.
That would be the volume.
Just the perimeter of the circle times the length. That strip.
There we go.
Perimeter. The perimeter from.
Oh, the edge of the circle times the
Yeah.
length? Okay.
Yeah. So this becomes my electric field at point P times 2 pi little r times big L is equal to L lambda over epsilon sub naught. And so now we can find the magnitude of my electric field. It's just going to be, well, L cancels out. I'm left with lambda over 2 pi r epsilon naught. Actually, usually written 2 pi epsilon naught. Since r is the variable. And then if you multiply, if I put charge at point P, we would get the force on the particle there, and then that should match what we did 2 weeks ago. Unless, of course, there's a Carroll's error in here.
This might be a really dumb question. Does epsilon have a representative value? Like, does it have a value it stands in for, or is it just a variable that represents?
Epsilon sub naught?
Yeah,
It has stands, matter of fact, it was on the flash quiz.
yeah.
Isn't that 8.85
That's the one.
times?
Do you remember the K value is 8.99 times
Yeah.
10 to the 9? You can figure out epsilon sub naught by using that 8.99 is equal to 1 over 4 pi epsilon sub naught. And then you just times it by 4 pi. And then
Well, times by 4 pi and then take the reciprocal.
yeah.
Or it also will turn out that, it's 1 over c squared times u sub naught. Yeah. Well, that's the permeability of free space. Not to be confused with the permittivity of free space. This is a measure of how a material or a medium is affected by an electric field. This is a measure of how it's affected by a magnetic field. This value is 4 pi times 10 to the -7th.
So permeability is magnetic?
Yeah.
Right.
Centimeters per meter, double check that. Anyway, these are all constants. This is officially defined by speed of light is fixed. That's a fixed number, and we calculate it that way.
The speed of light's involved in the magnetic stuff, but not the electrical stuff.
It is, I mean, they're,
Oh, it's all the same.
speed of light in the vacuum. We'll derive that later.
Oh, that's nice.
And then discuss why some physicists thought there was a mistake. Okay, so we did that one. Let's do the infinite sheet of charge now, which we did. We found the electric field from an infinite sheet or the force on a charge away from it. One or the other. We'll find the electric field coming from an infinite sheet of charge.
So before we were doing forces on the infinite line and sheets, and now we're doing fields?
Yes. Infinite sheet of charge with uniform surface charge density. Sigma. I know that sigma is equal to dQdA, which is going to be Q over some specific area. So once again, I'm going to create a Gaussian cylinder, except this time, roughly the same size. Ignoring this part of it, I have two cylinders here, and I'm going to create, and there's my infinite sheet. I'm going to create a Gaussian surface like that. So it's going all the way through. But it's some visualization before I subject you to my drawing. That's not the way that. And then on the other side. So it's a Gaussian cylinder that I have an equal amount of that cylinder on both sides of the sheet. that distance there. Or to make that big R. That distance there, little r. So a distance little r from the surface, what is the electric field at that point? Going through a very similar exercise over there, I've got a cylinder here, so I'm just gonna find the electric flux through the two end caps and then the side. So the electric flux through the left cap, plus the electric flux through the right cap, plus the electric flux through the side, is equal to my enclosed charge over epsilon sub 0. One more comment on the permittivity. I am assuming that there's nothing on either side of the sheet. It's the vacuum of space. It's classical physics, so we can assume that there really is a vacuum. So there's nothing on the other side, so the permittivity, that's what free space is. It's space absent of any material. If I stuck a material, if I had the sheet stuck between two dielectrics, then the epsilon sub naught would just become epsilon. And there'd be a specific value for that material. We will get into that. By symmetry, I know the electric field is pointing away from the sheet. I have an electric field pointing this way and that way. So which of these will have a flux of 0?
The side,
Why the side?
because it's perpendicular.
Area vector is pointing perpendicular to the side of the cylinder, which makes it parallel to the surface of this. Is indeed perpendicular to that. 0. Now the other two, my electric field is pointing away, so my electric field is pointing in that direction and pointing in that direction.